In Chapter 6, we introduced you to Maya's ability to control emitted particles through goal weights and offsets. In this chapter, we're going to investigate the use of goal offset to a greater extent. Goal offset allows you to change the position that a particle is trying to reach. An excellent example of this is the curve flow clip effect. Curve flow uses the RGB values of a ramp to store XYZ positions in world space, which, in turn, assigns the particle's goal offset to the resulting value. As the particle gets older, a different position in the ramp is sampled, which changes the goal offset and forces the particle to move forward. While you could achieve a similar result by driving the position attribute of the particle with the ramp directly, by using goal offset you get the added benefit of the internal Maya code for calculating how a particle reaches its goal. As we saw in Chapter 6, changing goal U and goal V enables your particles to flow across a NURB surface. By using parent U and parent V as well, your particles are able to remember their point of emission, not in world space, but in UV space. Therefore, if your surface emitter moves, your particles' relative positions are maintained. Any transformations you apply to your surface emitter are carried through to your goal and parent U and V attributes, even surface deformations. For this Pepsi commercial, we needed to have beads of water rolling down the surface of an aluminum can. Several techniques could have been used to animate the beads of condensation: keyframe animated geometry, motion paths, animated extrusions, animated texture maps, etc. We chose to use a dynamic simulation because it allowed us to implement control over the number of drips, their behavior as they rolled down the surface, and the length of each drip trail. I've opened the file ch8 Pepsi can base. In this scene, we have an animated can slamming down on a table. We want to make this can appear wet, so we're going to start by adding some water droplets to the can using surface emission as we saw in Chapter 6. Note how the emitted particles are being left behind. The particles need to stick to the can. To achieve this, we'll use goals. We'll also need to add the 4 standard goal per particle attributes, parent U and V, and goal U and V. Finally, remember to tell your particles to see their emitter as a goal object. Now we're ready to start working on our expressions. In my creation expression, I want to make sure the particle's goal is the same as its emission point. Now the particles stick to the surface. Next, we want to add motion to the particles so they appear as if they're streaming down the side of the can. If we turn on Display NURBS Components Surface Origins, we are given a visual indication of which direction the water will flow. Red indicates the U direction. We'll add a simple expression to our runtime expression, which will offset each particle's position in U over time. Now the particles move down the can. 0.1 is simply an arbitrary number. I would rather have control over how far each particle slides down the can in the space of a single frame. This way, I can reduce each drop's speed as it gets older, as it leaves more and more moisture in its water trail. To do this, I'll first have to add a per-object float attribute to my particles called drip speed. Then, we need to factor the can geometry parameter range in U into the particle's goal calculation. The per-object attribute drip speed is a float that we use to determine what percentage of the can's U parameter the drop moves per frame. With a drip speed of 2%, for example, the drop would take approximately 50 frames for it to slide from the very top of the can to the very bottom. I've set my drip speed to 1. I've replaced the old goal U change of 0.1 with this new goal U calculation. Now that we have water flowing down the can, we can add random zigzagging motion. We first need to explain how the motion will work. The animation will be based on a cycle of finding a new point as a target position, moving towards that point, reaching that point, then finding a new target. The cycle will repeat until the drop reaches the bottom of the can. How far away the new target position is and how quickly the particle reaches it can be defined as the drop's amplitude and frequency. We also need to figure out how to interpolate the particle between its current position and its next position. I'll begin by adding some per-particle attributes to my drops. I need to add target VPP, old target VPP, and target weight VPP. I'll also add 2 per-object attributes, amplitude and frequency. For this simulation, I'm going to control the amplitude and frequency of the motion on a per-object basis. I could easily assign random values to amplitude and frequency in the creation expression, but this simulation should incorporate enough random motion to fool the eye sufficiently. Remember, build your simulations from the ground up, only adding complexity where needed. More layered effects means longer debugging times, so try and keep your expressions as simple as your simulation will allow. When the particle is born, it needs an initial target, so it knows where to go right away. This target position will be a random position relative to where the particle currently is. Here, we've generated a random number based on the particle's birth position in v. The range for the random number is from position times 1 minus the amplitude to position times 1 plus the amplitude. The greater the amplitude, the further away the target could potentially be. For this simulation, we need to keep the amplitude fairly small. I'm using a number of 0.1 to start. We also need to give the particle a reference position for its old target, so we assign its old target VPP attribute to its birth position in v. Next, we'll modify the runtime expression to control how the particle moves in v to ultimately meet its target. As with the particle's movement in u, I need to make all values relative to the parameterization of the surface. I'll incorporate these values into the equations. When the particle has reached its target in v, we need to assign a new target. First, we need to constantly check if the particle has reached its target. Once the particle reaches its target in v, we store that value as old target VPP, then generate a new target as we did initially in the creation expression. In the last line of this if statement, we reset the particle's target weight, which is incremented later by the frequency. Now, the particle knows what to do when it reaches its target, but what happens in between? In the else half of this if statement, we need to increment goal v based on its frequency. To increment goal v, we'll use a smooth step function. This first line essentially takes the old target value and adds a number between 0 and the distance to the new target. We then increment the target weight by the frequency, which in this case is set to 0.2. Therefore, the drips will take 5 frames to reach their new targets. By implementing these three main attributes, frequency, amplitude, and drip speed, I have established control over how the particles move down the surface of the can. Notice how the particles all stream down the can without stopping. To simulate a real droplet of water, I would have to take into account dry spots on the can, which would slow the drip down. The first step towards simulating this level of realism is to give the particles random pauses in their descent down the side of the can. To do this, we'll need to add controls to describe how frequently the drips pause and how long they remain stationary. I'll use the per-particle attribute pauseCountPP to keep track of how long a particle has been motionless. We'll decrement this value until it reaches 0. Seeing as how pauseCountPP should be 0 when each particle is born, we'll initialize its value in the creation expression. We also need to initialize the particle's lifespan PP attributes, as we'll want the particles to die once they hit the bottom of the can. Make sure you set your particle's lifespan attribute to lifespan PP only. In the runtime expression, I'm going to kill off the drop particle when it reaches the bottom of the can. Now, in the runtime expression, we need to decrement pauseCountPP by a value of 1 for every frame. I've made sure to put these two lines at the top of the runtime expression, as I want the count to evaluate before the particle moves. Finally, if pauseCountPP is equal to 0, we need to reset it to a non-zero value. However, we won't pause the drip every time the count reaches 0. We'll use the rand function to decrease the probability of the drip pausing. First, we generate a random number between 0 and the per-object attribute pause frequency, which is set to 5. The ceil, or ceiling function, rounds any floating point numbers up to the next highest integer. This means there will be a 1 in 5 chance of getting through to the next step. In this if loop, we generate a random integer between the per-object attributes pauseMin and pauseMax time, which, in this simulation, are set to 2 and 10 respectively. The particle should be in motion only if pauseCountPP is less than or equal to 0. This conditional means I have to put most of my runtime expression under this statement. Note how I comment my close braces. This comes in handy when your if statements go beyond the height of your window. We now see the drops pause at random intervals throughout their descent. Another element I'd like to add to this simulation are trails of water following each lead drop. Instead of using emitters, we're going to use the emit command, which will let us emit particles only when the drop is moving and position them properly behind the lead drop. The most efficient way to use the emit command is to create new particles into an empty particle object. To do this, I simply use the particle command in the script editor. The -n flag names the particle object as it's created. This particle object follows the contours of the can in the same way as the drops, so we'll need to make the can a goal object for the trail particles as well. We'll also need to add the per particle attributes goal_u and goal_v. Now we add the emit command not to our trail particles, but to our drop particles runtime expression. This is a simple example of how to use the emit command. There's a few caveats to bear in mind, however. The -position flag only takes in 3 floats rather than a vector, so you have to capture the drop's position as a vector, then separate its 3 components into separate elements. The only other 2 attributes I'm assigning to the trail particles are their goal_u and goal_v, so they remain stuck to the can once they're emitted. Note that I had to place the float values in parentheses, as I need to evaluate the drop particle's current goal_u and v. If I play the simulation, you'll see a trail of particles left behind by the drops. These trails are quite sparse and regular, as I'm only emitting a single particle each frame. I want to be able to control how many particles are emitted per frame. There are a number of ways I could do this. 1. I could emit a set number of particles between the last goal target and the current goal target. However, if the particle moved a very small amount, too many particles would be emitted. Similarly, if the particle moved too much, too few particles would be emitted. 2. I could establish a relationship between how far each particle moves and the number of trail particles emitted. Using this second technique, I will get a consistent density of trail particles. So let's go ahead and implement it. First, I'll need to add a per object attribute to my drop particles called density. Now, in the drop's runtime expressions, I have to add 2 float variables which will store each particle's last goal_u and v positions. I'll add these variables at the beginning of the runtime expression before the new goal positions are evaluated. Now, we can define an integer based on the distance the particle moves over a single frame. This calculation is quite simple. In each direction, the particle's frame-to-frame distance in both u and v is calculated, added together, multiplied by the density attribute, and forced to be a positive number with the absolute value function. This number is the total number of particles that will be emitted each frame. Next, we create a for loop. This loop counts from 0 to the number of particles calculated using the density attribute. A float variable is established called $weight, which creates a larger number as the count gets higher. The reason we had to declare the float $if is because $I had already been declared as an integer. Mel operates in such a way that the result of a division is always the same data type as the numerator. Now that we have control over our trail particles' positioning, we have to modify the emit command in our runtime expression to accommodate the new values. Rather than execute the emit command for each time a trail particle is created, we're going to use a more streamlined approach. We're going to concatenate all of our particle position, goal_u, goal_v, and lifespan data into a single string, which will get evaluated only once for each drop particle. This provides us with a much faster solution than calling the emit command for each trail particle. To do this, we're going to use the eval function, which takes in a single string and executes it as mel code. To use the eval function, we first have to initialize a string, which will sit at the beginning of each emit command. This line sits outside of the for loop, which creates the trail particles. Next, inside the loop, we start adding to this string, which we'll evaluate after the loop. The syntax for assembling a string can be quite detailed. An easy way to see what you're creating is to print the string out to your script editor. However, I suggest printing out a single particle's emit string command. If we play the scene now, we can see the script editor spitting out data for particle ID 15. I'm happy with the way my emit string is being assembled, so I'm going to remove the line which prints the string and add a line that evaluates it as the last line in my runtime expression. Now we have water trails following each drop particle. For our final element, we're only going to render these trail particles. We're going to use a blobby rendering type for these water trails, as we'll have control over its surfacing threshold, which will make the particles appear to be a single stream of water. The most important aspect of blobby particles is their radius. To emulate the look of the trails following the lead drop in a single stream, I'm going to reduce the radius of each trail particle as it ages until it shrinks to a radius of 0. First, we have to change the particle render type of the trail particles to blobby. And we'll add the standard per object attributes for this particular render type. For now, we'll set radius to 0.3 and threshold to 0.4. The threshold attribute controls surface blending between each blobby's particle's surface, making adjacent particles appear as a single stream of water. A particle object's threshold attribute is quite important. Too low and your particles will appear as simple spheres. Too high and your particles will disappear altogether. I find it imperative to experiment and find a balance between your particle radius and threshold. An easy way to control the radius would be with a smooth step expression. However, a much more visual and interactive way to manipulate the streams would be to use a ramp. To do this, we first need to create a per particle attribute which will act as a multiplier to the particle's regular radius. We'll call it radius mult pp, and we'll add the same line to the trail particle's creation and runtime expressions. We'll also control each particle's individual radius with radius pp. We have nothing assigned to radius mult pp, so its values are being initialized as 0. I will now attach a ramp to the radius mult pp attribute by right mouse button clicking beside it in the trail particles attribute editor and selecting the pop-up menu item Create Ramp. To change the ramp, I'll right mouse button click in the same field and navigate to Edit Ramp. Now, when I play the simulation, you can see the particles shrinking in size. I can change the length of each water trail by changing the ramp's settings. In this ramp, the bottom represents the particle's birth and the top its death. Where the ramp is pure white, the particle receives 100% of its initial radius. As it grows older, its relative age moves up to the top of the ramp, which has a value of pure black, where it would receive 0% of its initial radius. If I change the ramp's values, I can shorten or lengthen the water trails.